Stefanos Panagiotou. I work as a machine learning engineer at Quadible. Today I will be talking about the user continuous behavioral authentication component, in brief called UCBA. This is part of the TANGO project's key exploitable results. It aims at transforming the digital identity authentication using AI and behavioral data. So in a nutshell, UCBA provides a novel component that allows the users to authenticate to the TANGO platform and other third-party services by leveraging behavioral patterns of the users and thus enabling the continuous assessment of their authenticity. So in today's presentation, I will first give a short introduction to what UCBA is and why it matters. And then I will walk through the technical outline of this component and finally show some examples of the component's actual usage. So let's begin by looking at the current landscape of the user authentication domain and the challenges it presents. As we know, we are witnessing a continuous rise in digital fraud, a trend that has accelerated dramatically during and after the COVID-19 pandemic, since the majority of services moved online. So we are living in a time where cyber threats are not only increasing in volume, but also they are more sophisticated, and passwords are routinely stolen. We have phishing attacks on the rise, and credential stuffing is more and more common nowadays. So the current state of the art in the authentication field consists mainly of the authentication through a sequence of numbers, in other words, passcodes or PIN codes. We have also authentication through a pattern or a graphical-based password, or two-factor or multi-factor authentication, and also individual biometrics-based authentication. However, all these authentication methods mentioned require users to remember things or to make actively certain actions. Another important issue is that users do not often have any control over the databases in which the information they are using to authenticate is stored. Therefore, there is this important issue of the data privacy. Usernames, passwords, or biometric data such as fingerprints, iris, face, or voice can be compromised, and in this way violate the user's privacy. So considering the previous challenges, the continuous behavioral authentication approach offers a fundamentally different aspect with dynamic and ongoing user verification. So our behavioral authentication system that is proposed is cost-effective and passive. That means that it runs silently in the background of the web or the mobile application. So another important aspect is that it is frictionless. This means that the user experience remains smooth. And of course, it's incredibly hard to disprove. Overall, this solution is designed to be lightweight and scalable. It can be integrated into web applications or enterprise systems or whatever mobile platforms available. So no extra hardware is required. Moving on to the second part, I will proceed to display how the system works at a higher technical level. So as previously mentioned, the UCBA component enables the continuous assessment of the user when he is accessing a mobile or a web application. During this time, the system collects various behavioral elements that can uniquely identify an individual. So when these elements are combined, they can offer a high degree of confidence regarding if the legitimate user is assessing the particular application or if an imposter user is currently logged in. The data that we are using can be discriminated between the web and the mobile applications. So on the web part, we collect data like how fast the users are typing, how long they are holding down each key in the keyboard, how fast and how much they accelerate their mouse movements. We also collect data from the location of the user, the device information, and the network information. Furthermore, we are, where possible and where applicable, transaction and usage data are recorded, and if available, any fingerprints or faces that are used during facial recognition. So these signals may seem insignificant at the first sight, but together they form a behavioral signature that is as unique as a biometric fingerprint. In the mobile scenario, we go deeper. We can measure the swipe speed, the touch pressure, and even how often the users rotate their phones. So for this case, we use smartphone sensor data from gyroscopes, magnetometers, and accelerometers that can detect these unique user patterns. And this level of data variation makes the impersonation extremely difficult. And of course, all of this is powered by AI in the background. Our system uses machine learning models that can learn the user's pattern over time. And in this slide, we have a closer look at this workflow. So first of all, we are collecting the data, as previously mentioned. There are no extra steps or interruptions for the user. So the user experience remains intact. Furthermore, we proceed with the necessary feature extraction. So the raw data collected is filtered and normalized, and afterwards informative features are derived from these raw behavioral signals for its modalities, such as the typing modality, the mouse movements, or the smartphone sensor data. So the purpose of using these features is to help represent accurately the user's behavioral patterns. And then we have the model training and the inference actions. So the models are periodically updated to accommodate any changes in user behavior over time. And this improves the long-term reliability and helps to mitigate data drift scenarios. And to accomplish this continuous user authentication context, we employ different techniques that are based on traditional machine learning algorithms and modern neural networks in order to classify the users, if the user is genuine or not, as a binary classification, or we provide anomaly scoring by calculating the deviation from the user's trained profile. And then for the decision-making part, the last part, this AI-based system compares the user's current behavior to his already logged patterns from his previous sessions and interactions with the system. And then it generates a risk score, which is exposed to the related system of the end user in order for the relevant stakeholders to take the appropriate access, either to maintain access or to trigger follow-up authentication, or even to lock the session or alert the system and administrators. The software artifacts behind the UCBA component comprise of two main artifacts. and one additional that is developed for demonstration purposes. So first of all, we have the software development kit. So this SDK is responsible for the data collection and the data offloading to the backend component. This SDK, of course, supports both mobile and web interfaces, and it is integrated with the host applications that are about to be protected in order to ensure that during the access of the user to the particular application, the component is able to continuously collect the data and assess if the user that is interacting with this application is legitimate or not. Then we have the backend component, which provides all the processing and inference capabilities through the secure communication channel that is established with the data collection SDK. The backend retrieves the appropriate information from the client in order to feed the behavioral models and fuse all this information in order to generate the risk score. So the backend component has been developed to be deployed on Kubernetes and combined with Docker images of each of the behavioral trait components. And then for the demonstration of this technology, a demo banking application has been developed in order to showcase the user experience and at the same time utilize it for testing and validating the user the UCBA component. So this demo banking app incorporates common functionality that is provided by the majority of the banking apps. For example, checking the balance of the account, providing a list of the transactions performed by the owner of the account, either incoming or outbound, and showing the details of the transaction that has been performed. So at the end, the scope of this demo application is to collect the data and transmit it to the backend component in order to proceed to the model training and inference for the decision-making engine. At this point, it is also important to note that we recognize, of course, the importance of user privacy. We ensure that all data is stored and processed within the European Union to maintain compliance with GDPR requirements. Of course, we employ data normalization techniques to remove any personally identifiable information, and security is enforced at both the device and infrastructure levels. We use advanced encryption protocols during data transmission and storage to reduce the risk from breaches or unauthorized access. And at last, our systems are ISO certified with internationally recognized standards in order to demonstrate our commitment to the best practices in information security. And it is also very important to note that one of the strengths of this solution is the ease of deployment. So it's implemented through simple SDKs, as described, or browser-based scripts that require little to no changes in the end-user system architecture and implementation. So it becomes highly scalable across industries, either in banking, finance, or healthcare, e-commerce, and public organizations. And moving on to the third and last part of this presentation, I'll walk through some examples of real use cases that demonstrates how UCBA works in action in real life. So first of all, this is a dashboard that shows in real time the sessions that are recording in the system. Each row represents a user login attempt with identifiers and access method, either web or mobile. And this provides insight into the access channel from the user, which later can be used as a risk signal from the backend. So this view displays how we can detect fraud using this layered approach that combines behavioral patterns, device information, and biometrics. The fraud status flags risk, any risk that can be present, such as imposter behavior, SIM swapping, or any promo abuse. So the behavioral patterns analyze typing and interaction style, and the red icons represent anomalies in this session, while the green bars indicate trusted behavior. So even when a user logs in from a new device, if the behavior and biometrics align, the system can still mark as legit. So this approach allows for real-time fraud detection that has minimal friction for the genuine users. If we want to dive into a specific session from a connected web application, as in this example, we can observe for each modality or otherwise an authenticator, and for each particular time window and specific time frame in his session, we can observe the reaction from each behavioral component. So each dot in the timeline represents a specific window that has usually a duration of 15 seconds. The green dots represent a positive score for a given anomaly, for a given modality, while red dots represent a negative score, and the gray dots represent that more data are needed in order to infer results from the machine learning models. In this case, we have suspicious gestures and unfamiliar typing rhythm. The system detects this deviation and flags it as a high risk. So depending on the policy of the end user, this can result in re-authentication or a session lockout. On the other side, this is an opposite example. The user's behavior is consistent across typing activity and gestures. So the system is confident that the user is genuine and access can be maintained without any interruption. And this concludes the presentation for the UCBA component. The audience can reach out with any questions or any feedback in the following email in this slide. Thank you very much for your attention.